Hello, so today is about the normal model. So today you are going to be able to use a z-score, z-table to estimate the area under a normal curve, and then you'll be able to calculate percentiles of a distribution that is approximately normal. So let's start with talking about what a normal model actually is. So a normal model is a numerical distribution that is unimodal and symmetric. So here is a couple of examples of what a normal model would look like. These are what we call density curves, which means instead of seeing each individual bar like on a histogram, we're seeing the overall shape of the graph. Right? So anything that is unimodal and symmetric, so it doesn't matter how wide or narrow the graph is, it only matters that it's unimodal and symmetric. So if we have a numerical distribution that is approximately, or is unimodal and roughly or approximately symmetric, then we can use the normal model in that situation to estimate percentages, which is a lot of what we do. In real life, our distributions are rarely perfectly symmetric, so we kind of say the words roughly normal, meaning that it is unimodal and roughly symmetric. So let's go back to our discussion of walrus weights from the lesson we did in class. So adult female walrus weights are approximately normally distributed, that's what that says, with a mean of 812 kilograms and a standard deviation of 67 kilograms. So the first thing we're going to do is draw and label a normal model for these female walrus weights. I'm going to start by kind of drawing a normal model shape. It doesn't have to be perfect. Clearly my normal model could use some work. I'm going to go ahead and draw a line down the middle. This is the kind of where the peak is. This would be where the mean is. So I'm going to go ahead and label 812 for the mean. And then in a normal model, from the mean to the very kind of left end and from the mean to the right end is about 3 standard deviations. Maybe not exactly, and there definitely can be some data further than that, either direction, but the majority of the data is going to fit within about 3 standard deviations. So to figure out what those other numbers are and to label those other numbers, I'm going to use the standard deviation number. So for example, to figure out what this number is right here, 812 plus 67 would be that number, which is 879. I can do math in my head. And then if I add 67 again, that gives me this number. And then if I add 67 again, that gives me this number. On the left side of the graph, if I do 812 minus 67, that's going to give me this number. Minus 67 gives me that number. Minus 67 gives me that number. So I'm going to go ahead and figure out what those numbers are. Oops. And then I will come back. So there is my normal model drawn and labeled. So what does this normal model do for us? So one of the things that we know about any distribution that is roughly normal, but especially for the actual normal model, which is perfect, what we know is that in a normal model, 68% of the observations that we're distributing, that we're dealing with in this numerical distribution, 68% of the observations will fall within 1 standard deviation of the mean. So from 1 standard deviation below to 1 standard deviation above should contain about 68% of our observations. Further, within 2 standard deviations of the mean holds about 95% of our observations. And within 3 standard deviations of the mean is 99.7. So almost all of our observations will fall within 3 standard deviation. So the 0.3% that's left over will kind of fall beyond 3 standard deviations either way. Okay, so we call that the empirical rule, or sometimes I like to call it the 68, 95, 99.7 rule, which is harder to say, but it's more useful as a name. So 68% within 1, 95% within 2, 99.7 within 3. So a couple quick facts about the normal model, and then we'll kind of make sense of this in terms of the walrus weights and what that tells us. Okay, so the total area under the entire normal curve is 100%. So the entire normal curve from all the way to the left to all the way to the right, the entire area underneath there is 100%. But in theory, the normal curve extends forever in both directions. So the height of that curve never actually reaches zero. It's like an asymptote situation on both sides. So when we do some of the math that we're going to do to figure things out, we have to keep that in mind. So in this example, still talking about walrus weights, I have a lovely little drawing here that has everything labeled, and then I have my little empirical rule kind of put in there as well. So what proportion or what percent of female walrus weights is between 812 and 879? So if I look at that, 812 is here and 879 is here. And I'm trying to find out what proportion or percent of walruses weigh between those two numbers. So remember, our empirical rule tells us that from one standard deviation below, which is here, to one standard deviation above, that's 68%. And because a normal model is perfectly symmetric, we know that this part right here that I've shaded should be half of that total 68% because it's symmetric. It's the same on both sides of the mean. So I just need to figure out what is half of 68%, and I'll have my answer, which is 34%. Right? So I'm using that empirical rule to figure out some things about this situation, about this distribution. So let's try another one. So this one says, what proportion of female walrus weights is less than 879? So now I'm talking about, here's 879, and then I just want less than. So I mean, I want the entire distribution. I want all the walruses that weigh at anything less than 879. So not just down to 611, completely, even walruses that weigh less than that. So this one I'm going to kind of divide up into two little sections here. So we already did this part right here in the last example. We know this part right here was half of 68, which was 34. Now this left section is basically half of the graph, right? It's everything less than the mean all the way down to forever. So this part over here is 50%. So if I add those together, I should get the total area. 50 plus 34 is 84. So there's a lot of things I can figure out. There's a lot of percentages I can figure out just by looking at this empirical rule. I'm going to do one more example. So for example, if I wanted between 745, which is here, and then 946, which is here, I could do some fun math to figure that out. I always like to work from the middle when I'm doing this kind of like fancy math. So this right here, this little section is going to be the half of 68, which is 34. And then this section right there is basically, that's 2 standard deviations from the mean. So if I remember, my 95% is within from 2 below to 2 above, and this is half of that. So I could say that's half of 95, right? Figure out what half of 95 is, add it to 34, and that is your answer. I'll go ahead and figure what that is. I should have done this before. So half of 95, it's 47.5 plus 34 is 81.5. So this right here, that part right there was 47.5%. So if we add those together, we get 81.5%. Right? So we can do a lot of little tricky things with the math just by knowing that 68, 95, 99.7 rule. I can use lots of fun addition, subtraction, dividing, etc. So I'm not even going to do those other two examples. Right? What I want to get to is that at some point that's going to break down. So this question asks, what percent or what proportion of female walrus weights is less than 600? Well, 600 is not one of my like perfect, nice standard deviation numbers. 600 is less than 611. We're way down here now. So I could kind of estimate based on where that is. I could use the 68, 95, 99.7 rule, figure out what proportion is less than 611, and then I could kind of say, well, it's less than that because it's a smaller area. But if I want to find an exact rule, I'm going to have to use some other method of figuring this out. Okay? So we could use calculus. This right here on your screen, do not write this down. You do not need to know this, but this right here on your screen is the formula for that normal curve. So the actual formula that creates a normal curve. So we could use calculus to find the integral, to find the area under the normal curve up to a certain point, and that would work. But that sounds real not nice or fun in any way. So instead, we will use what we call the z-table. So the z-table is a table, as you could imagine, that gives us basically a whole bunch of areas or proportions under this normal curve up to a certain z-score. So remember from last time, a z-score is basically telling us how many standard deviations from the mean we are. So basically, someone did all the calculus for us for all of these z-scores throughout the normal model and then put them in a table for us. And that's what we're going to use to find most of our proportions or areas under the curve. So let's go back to that question of what proportion or what percent of female walrus weights is less than 600 kilograms. So I'm down here, 600. So first step you should always do is draw and shade your normal model. We're in unprecedented times right now. We're using a lot of computers. When you get to AP exam and you're actually writing things out, you will need to draw and shade your normal model to get credit. That is how you show your work. So probably for these couple of questions on this test, I might have you draw it on a sheet of paper and take a picture of it and turn it in, because that is how important it is. So we have our kind of area shaded. The first step we're going to do is actually calculate what is the z-score for 600. So remember, z-score is the observed value, which in this case is 600, minus the mean, which is 812, divided by the standard deviation, which is 67. And this is basically telling us how far from the mean, or how many standard deviations from the mean is this value. So I'm going to do this in my calculator. Make sure you do the subtracting first and then divide. Comes out to negative 3.16. Okay? So negative 3.16 is my z-score that corresponds to that place on the normal model. That's kind of our standardized score on the normal model. Okay, so once I have that z-score, I'm going to go and I'm going to open up my z-table, which looks something like this. So your z-table is giving us the area, the percentage that is below or to the left of a certain z-score. So I have a whole bunch of numbers along the left-hand column and upper row. That is basically z-scores. The inside of the table has proportions that we could either leave as proportions, as decimals, or we can turn into percents. So the first page is going to have all of your z-scores that are to the left of the mean. Your second page has all the z-scores that are to the right of the mean. Notice that these graphs at the top tell us that the area you're being given, or the probability you're being given, is the area to the left of your z-score. So keep that in mind. So what I would do, my z-score again was negative 3.16. So what I'm going to do is I'm going to look up that z-score by looking at the left-hand column and the upper row. So I'm going to look for the first decimal place first. So I'm looking along my left-hand column for negative 3.1, which is right here. And then the upper row is getting us that second decimal place. So we want negative 3.16. So I'm going to go over to this 6 column, and then I'm going to line that up. So negative 3.1, and then we want to be underneath the 0.06 for that second decimal place of 6. So the area that the z-table is telling me is 0.0008. So going back to my example, the area that we got from the z-table is 0.0008. So that is the proportion of walruses, or female walruses, that weigh less than 600 kilograms. Now we could convert that into a percentage by either multiplying by 100 or moving our decimal place over twice. So that would tell us there's 0.08% of walruses that weigh less than 600 kilograms. Either is appropriate right now. I do not care one way or the other. AP exam does not care one way or another whether you give them a proportion or a percent. So either is fine. All right, let's practice another one for funsies. So this one says, what proportion of female walrus weights is more than 780. So again, your first step is to draw your normal model. When you are drawing these on your paper, you're going to draw them separately for each question. Don't try to draw one and do the same thing. So in terms of labeling, I would always say label the mean. It's really important. You don't have to put these standard deviation numbers on there every time, but at least label the mean, and then at least label the number that you are dealing with in this problem. So I'm going to label 780, right? So at least I know what value I'm dealing with. And then we want more than 780. So I'm going to go shade to the right of that for that area. Okay. Part of the reason that we shade the graph is it gives us somewhat of a visual representation of more or less what area we should be getting. So I can see from this, from what I've shaded, that my answer that I get should be more than 0.5, more than 50%, because I clearly shaded more than 50% of the graph, right? So same thing as last time, I'm going to start by finding a z-score. So I'm going to do z-score equals 780 minus my mean of 812 divided by my standard deviation of 67. Figure out what that equals, which is negative 0.47 or 48, I guess, if we round it. Yeah, 48. Okay. So I've got my z-score. So now, again, I'm going to go to my z-table over here. And I'm going to find, I already forgot it, negative 0.48. So I'm going to go down here. So I have my negative 0.4 right there. And then I need to go until I'm underneath the 0.08 column, which is the second to last one. And I have this proportion. So negative 0.48 is 0.3156. So going back to my problem, the area I got from the z-table is 0.3156, which would be 31.56%. But hold on, remember, our graph is showing us what to expect. So clearly I shaded more than half of the graph, and this is not a proportion that represents more than half. So remember, your z-table automatically is giving you the area that is less than your z-score, or to the left. If we are on a problem like this one, where I don't want the less than, I want the more than, I have to do a little adjustment at the end to make this work. So I'm going to do 1 minus, or you could think of this as 100%, because 100% is under the entire graph, minus 31.56%, which is this area over here. Basically, our z-table just told us the left side area. So if I subtract that from 1 or from 100%, that's how I get my answer. 0.6844, I'm videoing. Everybody say hi to Miss Bowman. Okay, so 0.6844 is our answer there. All right, let's do another type. This one's saying what proportion of female walrus weights is between 700 and 800. So again, I'm going to draw and label my normal model. Make sure you at least label the mean and the numbers that you're dealing with. I did that wrong. 700 is down here. There we go. So I'm going to shade. All right, so the way we do a between is we're still going to start by finding z-scores. So I'm going to go ahead and find my z-score for 700 and my z-score for 800. It's the same way I've done before. Okay, I'm going to figure out what those are and come back. So those are our z-scores. So I just found 2 separate z-scores. Now I'm going to go back to my z-table, and I'm going to look up the proportions for both of those separately. So I'm going to my z-table, and I'm finding negative 1.67 or 7. It's right here. So negative 1.67 is 0.0475. And for negative 0.18, would be 0.4286. To find the area in between, what I do is I subtract, which gives me 0.3811. So the reason we subtract, I'm going to kind of show this for you. So when I find the z-score for 800, and I find that area in my table, in my z-table, that is telling me the entire area of the graph that is to the left of the 800. but I don't want that whole area. So I go back and I find my z-score for 700 and find that area, and that's giving me the entire area to the left of 700. So what I'm doing is I'm subtracting this big highlighted yellow area minus this kind of black shaded area, and I'm left with that area that's in between. So that is always how I will deal with the in-between numbers. Right, we're going to do one more practice for in between. So what I'm going to do is ask you to pause the video so you can practice this one, see if you get an answer, and then you can, in about 5 seconds, I'll put the answer up and you can check it. All right, so there is our answer. So you can check yourself. One thing I do want to mention is if you are doing this and you kind of round slightly differently or you round incorrectly, which causes you to get a slightly different number on your proportion from the z-score, and so you get a slightly different end answer, that is okay. AP exam is very, very lenient in terms of like small differences in decimal place. And as long as we can see all of your work, including showing your z-score, make sure you write z equals, and then showing your normal model drawn and shaded, those are not things your LV will get counted off for. So I wanted to mention that as well. So there is your answer for that one. Okay, so last little topic for today is we're going to look at how we might use the z-table backwards to answer kind of an opposite question. So in other words, if we know the proportion or percent that we want, and we want to find the value, or for the walrus example, the weight that would give us that proportion, we're doing everything backwards. So this is the kind of question that we'll ask about things like percentiles. So this up here, it kind of got cut off, says what z-score corresponds with the 60th percentile. So percentile is basically the place in the graph or the place in the distribution where 60% of the data is below that value. So the what I'm looking for in my z-table, right, is I would look at, remember the z-scores are on the edges. Inside the graph is the proportion or percentage. So if we want there to be 60% to the left or below the z-score, what I'm going to do is I'm using my z-table backwards. I'm looking inside where the proportions are and trying to find the closest I can get to 0.6, which is 60%. I say the closest because for this type of problem, right, we're not going to necessarily have an exact 60%. So I'm looking for 0.6 or as close as I can get to it, which is somewhere between these two numbers. So for a problem like this, technically we would pick the one that's closest, which is this one on the left. But if you gave me the z-score for this one on the right, again, that's not something I'm going to count off for because it's close. But technically it'd be this one because it's closer. So 0.5987 is about as close as we can get to 0.6. So I'm going to find what that z-score is. So that z-score is 0.25. So that would be the z-score that corresponds with the 60th percentile. For the 10th percentile, which is the second question, right, it's the same idea, but now I'm looking for 10% or 0.1. So again, I'm going to go and notice that my proportions on this part of on the inside of the graph are in order from biggest to smallest. That makes it a little bit easier. So I'm looking for 0.1 or as close as I can get to it. So I have 0.1075, 1056, 1038, 1020. Here's 0.1003. I think that's about as close as we're going to get. So once we find it inside the z-table where the proportions are, I'm going to find what that z-score is. So negative 1.28 would be that z-score. So let's look at a type of problem where I would actually have to use that information to figure something out. So, still talking about the walruses, says approximately what weight represents the cutoff for the bottom 20%. So I'm going to draw a quick graph. On the problem like this, you don't have to draw a graph and shade it, but I find it helpful. So, right, we still have our mean of 812, and we want to know what is this value, what is this weight right here, where the area or the proportion less than that is 20%. So we're kind of doing everything backwards. So all of the steps that we did before to find the percentage or the proportion, we're going to work backwards. So my first step is to look on my z-table to figure out what z-score would give me that 20%. So again, I'm going to go to my z-table. I'm going to find as close as I can get to 0.2, which is 20%, which is this one right here. So 0.2005. And then once I find that, I'm going to look at what z-score that is. So negative 0.8 or negative 0.84. So negative 0.84 is my z-score. Right? And then once you find that z-score, we're continuing to work backwards. Now I can set this up with my equation for a z-score. So we know a z-score, which is negative 0.84, is equal to the observed value, which is the thing I don't know, minus the mean divided by the standard deviation, right? And then at this point, we're just doing some algebra. So I'm going to multiply by 67 on both sides, which gives me negative 56.28 on this left side. And then on the right side, obviously the 67s would cancel out. So x minus 812. And then I would add 812 on both sides to get the x by itself. And that gives me 755.72. Remember, on these types of problems, we're dealing with a weight, so you need to put a unit on it. So on this type of problem where you're working backwards, you need to put a unit on your answer. So that means that walruses that are about 20% of walruses weigh 755.72 kilograms or less. So that is how we do backwards. All right, I'm going to do one more practice. Let's say we were asked approximately what weight represents the cutoff for the top 5%. So again, I'm going to draw a picture because that helps. So this one's a little trickier. Remember, our z-table does not give us a greater than area ever. It always gives us less than. So for this problem, I would suggest, right, thinking of what's below that. So we want 5% above, which means we want 95% below. So my first step, again, is to go to my z-table and find 0.95, or as close as I can get to it. So I'm looking. So we have 0.9495, 0.9505. So this is one where your two options are pretty much exactly equally distant from 0.95. So you could use either one. Technically, we would round up to the higher z-score, but you know. So I'm going to use 1.65. Notice that we're on the upper end of the table, which is why we have a positive z-score. It's another good way to check. So 1.65 equals x is the observed value that I don't know, minus 812 divided by 67, 922.55 kilograms. Okay, so my suggestion on questions like these and in this stuff in general is use your common sense, draw the picture. So if we're talking about the top 5%, my answer should be above the mean. That makes sense. So if you're getting a value that is below the mean, something went wrong. Probably it's that you forgot to do the whole 1 minus situation. So just be very, very careful on a question like this. One last example. And again, I would suggest pausing the video, reading through it, trying to figure out if you can figure out what to do. And then in about 5 seconds, I'm going to put up the answer. All right, so here is our answer. As you can see, we had to start off finding a z-score by using the idea of percentiles, just like we did on the last example. But on this one, we knew the observed weight was 20. We know the mean weight is 16.5, and what we're looking for, what we're solving for, is the standard deviation. So it's a little bit different, but it's a similar process as on that last example. All right, I'm going to go ahead and call it quits for today, when we will come back next class and practice more with the normal model. All right, go team.